Good afternoon, everyone, and thank you for joining for our webinar on the future of quantum computing, where we'll dig deeper into Microsoft's announcement about their topological quantum breakthrough. My name is Jörg van Inge. I'm the CEO and co-founder here at GetFocus, and I'm joined today by...
Hello, everyone. I'm Martina, and I'm an analyst here at GetFocus.
Next. Right, so today we'll briefly introduce you into what we've done. We'll run you through the forecasting methodology because it's important that you understand how this works in order for you to have an understanding of what our forecasts mean. Then we'll take a look at our quantum computing report. And finally, Martina will take you through some insights on the platform, after which we'll open it up for Q&A. And if you have any questions, please drop them in the chat and we'll make sure to address them. Right, so generally speaking, GetFocus works with heads of R&D in all sorts of industries. We help them make forecasts about which technologies are going to dominate in their industry long before it's obvious. And the main problem that we help solve is the following. There's exponentially more emerging technology across time, which makes it harder and harder to keep up with everything that's happening in every space, especially because the amount of time that it takes to do so and to really learn about what's going on hasn't really changed. And that leaves you in a situation where the puzzle is growing faster than you can lay down the pieces. To address this issue, we've developed a method that does four things. First of all, we have AI models that can help you scout what are all the emerging technologies in a certain space, such as in quantum computing, which we'll be doing later. We can evaluate those technologies again using AI, churning through endless amounts of patent data to learn about the upsides, the downsides, the state of the art of this particular technology. Then we can predict which technology is going to dominate in the future based on how fast it is getting better. And finally, we can do deep dives into those domains to learn about all the details in that particular field of technology. And we can also help you monitor those areas. And the key question is, how on earth can you predict which technologies are going to win? And before we look at quantum, I'd like to explain to you how this works. So back in 2018, we collaborated with MIT to build the world's first technology forecasting system. And MIT has had a research institute that has been studying technological change for about 30 years. And they ask questions like, why does one technology win? Why does the other one lose? What is Moore's law, etc. And at some point, they realized that they had lots of ideas about this, but they didn't have any data to prove whether any of the theories were correct or not. So they figured, let's empirically measure how quickly these 28 domains of technology spanning all sorts of industries have improved over time. So what that entails is you create a key performance indicator for a particular field of technology that reflects the trade-off between performance and cost. And you measure how fast that got better with all the devices or technology that was on the market within that particular domain. So here's an example of what that looks like in the case of hard drives. So the purpose of a hard drive is to store information, which we can measure in gigabytes. And the cost of a hard drive, obviously, we can measure in dollars. And note that the y-axis here is logarithmic. So whereas this looks like linear progress, we are in fact talking about exponential technological progress. And also note that that progress is relatively consistent over time. So what MIT found is that every field of technology they measured showed exponential progress with a relatively consistent percentage year over year. And this percentage dictates how fast the technology can get better. And the easiest way to think of them is as interest on a bank account. So if you have a 3% interest rate on your bank account, because of the compounding nature of interest rates, the absolute amount of money on your bank account will go up exponentially. But if you get a 65% interest rate on your bank account, it will still go up exponentially, but much, much, much faster. And so the key driver of which technology is going to win isn't how it's performing today, but it's about how fast it gets better. So the next question became, can we somehow predict this? Because measuring this by hand took about 6 years, which doesn't scale. It's not very feasible. It's also not very fun to do because it means looking at endless amounts of spec sheets, digging through the internet, research papers, etc. And that's when we started thinking about patent data. So why patents? Well, before it's on the market, it's typically already described in patents. Almost everything you can possibly imagine is patented in one way or another. And even things that are not patented, such as open source software, are typically mentioned in patents. So by searching for a term like RISC-V for open source software, you can still create a data set that represents that technology, even though it's not directly patented. Probably the only thing that is funny about patents is that they're the only thing that we agree on globally. Back in the late 1800s, the whole world came together. They agreed on how to internationally standardize the IP system. That means that a patent in China looks basically the same as one in the US, Japan, Korea. Doesn't matter. They all have the same structure and they follow the same rules. And because it's so well structured, it's perfect for AI because AI loves well-structured information. If we take a high-level view on what is actually in a patent, people tend to think of them as legal documents, which they are, but also if you read one, it doesn't make much sense because the vast majority of the information is very dense, detailed, technical information. But at a high level, you basically say 4 things in an individual patent. You say, here's what I've invented, this is what I'm improving over, and you cite back the prior inventions that solved the problem in some older way. Then you say why yours is better. And finally, you have a really long description of how it works in detail. And especially point 2, the citations are crucial because they form the backbone of our forecasting model. So imagine here in 2019, we've invented something. And we refer back to an older invention from 2014. That means that apparently it took 5 years for us to come up with the next step for this field of technology. This we call cycle time. And the easiest way to think of it is as how quickly does a technology take steps forward. The next thing we measure is as soon as there is a new generation of knowledge, how much does it get cited by subsequent steps, which tells you something about the magnitude of the step forward. This we call knowledge flow. And the easiest way to think of it is as how big are the steps. So how quick are the steps? How big are the steps? Turns out that if you're able to find every single invention that relates to the entire historical development of a field of technology, like, for instance, for all these different types of quantum computers, and you measure the knowledge flow and the cycle time over time, that you can very accurately estimate what the rate of improvement is for that technology without empirically measuring it. Because based on the MIT data, it turns out that technologies that improve fast have short cycle times and high knowledge flow. So they take quick, big steps. And technologies that improve slowly have very long cycle times and they have low knowledge flow. So they take slow, small steps. And with that said, let's take a look at what's emerging in quantum and what our improvement rates say about what the future of quantum will be.
So let's start by introducing the star of the show, which are Majorana particles. These particles are extremely exotic, and that's because they exist as their own antiparticle. And that means that unlike traditional particles that have a counterpart, like for example, protons and electrons, Majorana particles are perfectly self-dual, so they exist as their own counterpart. And since they were first theorized by Hector and Majorana in 1937, the world has been waiting for a quantum computing technology that could actually use Majorana particles. This is until Microsoft declared that they have created a new state of matter in the field of topological superconductivity, and this new state of matter is called topoconductor, which is a special material designed to host technological quantum states, like, for example, Majorana zero modes. But the road to this announcement was not always so smooth, because in 2018, Microsoft first claimed that they had discovered the existence of Majorana modes in the nature, but then the statement was later retracted, and this started to create some doubts over Microsoft development. But Microsoft continued to develop their innovation until in 2025, they finally came up with their Majorana 1 chip. Now, the scientific community is divided about this announcement. Some are excited, some are skeptical, but nonetheless, it's still a step forward in the quantum computing race. Speaking of which, we should introduce who are all the protagonists of this race, because quantum computing based on Majorana particles is not the only contender. So we have superconducting qubits, which are basically tiny electrical circuits that are made from materials that have almost no resistance at very low temperature, which is usually close to absolute zero. And they conduct current in special quantum way to act as qubits. Then we have neutral atoms, which are individual atoms that are not electrically charged, and laser can be used to trap and move these atoms to store and process quantum information. Then we have photonic quantum computing, which is a method that uses photons, so particles of light, as qubits. And photons can travel through fiber optics and mirrors in order to perform quantum operations. Then we have trapped ion qubits, which are ions, so atoms that they have a charge and are held in place using electrical fields and can be manipulated with laser to perform quantum logic. And then last but certainly not least, the topological qubits, which are special kind of qubits that are designed to be naturally shielded from error. And this is because instead of storing information in a single fragile particle that can be easily disturbed by environmental noise, they store information in the overall shape and pattern that the Majorana particle takes. So the information are basically stored in the quantum connections, and therefore they are less prone to errors. But now the big question is, which one of these technology is actually going to take the lead and be the future of quantum computing? And to answer this question, we can move to our platform, where I can show you in real time how our analysis usually work. So what we can start with is, initially, when we want to learn more about the technological domain that we want to investigate, we can go to our feature that is called technology scouting and search for a technology that we are interested in. So, for example, superconducting qubits. And now you can see that the AI prompt us with interesting technologies that are relevant to the area that we are interested in. And what we can do is take one of these technology and perform a search in the patent landscape. So now our AI will read through global patent data to retrieve all the patents that are specifically related to our topic. And it will take a moment to process, but the result will be a comprehensive data set of all the relevant patents that are related to our technology. Here we go. So in this case, we have this data set, a little bit over 7,700 patents. And what we can see is the improvement rate of the technology. But this information in of itself doesn't give us much insight, because the true power of improvement rates is shown when we compare different technologies with each other. So for you, I already prepared a data set with all the main qubits technology that I will introduced on the slides. And by comparing them, we can understand which one is actually improving faster. And then, as you can tell from the graph, topological qubits are improving the faster, which is a confirmation that Microsoft is perhaps investing in the right direction. But since there have been so many controversy surrounding Microsoft's true capabilities of creating the right condition to host Majorana particles, we can actually do another analysis that can help us understand whether Microsoft is indeed going in the right direction. And this analysis...
Maybe before we move on, if you just compare one more time. Right. So just a little bit more about these improvement rates. Whether the line goes up or down doesn't really matter all that much, as long as one contender is higher than the other. So similarly to where you would put money in which savings account, you would want the account that pays the best return on your money. And the percentage basically indicates, in this case, which technology is making progress the fastest. So just because topological qubits are on top doesn't mean that they're the best today, and that it will for sure blow everything out of the water tomorrow immediately. Nevertheless, it means that they're progressing faster, and we can tell this if you open up the cycle time and the knowledge flow.
Yes.
Because in this case, also topological has one of the lowest cycle times, which means that in this case, 4.5 years or so, a new generation of inventions is published, which is faster than most others. Only neutral atoms are coming close, but of course, there's a fair amount of synergy between neutral atoms and topological qubits. And then if we go down to the knowledge flow, and then also topological is among the top contenders when it comes to knowledge flow, which means that these inventions are getting cited more than others, and even more than, for example, superconducting qubits, which is interesting because that field is much larger, and so there is much more to cite. That means you might expect there would be more citing there. But another interesting thing that we found is that the number of inventions doesn't relate to improvement rates whatsoever. So most of the time when people look for technological trends, they'll look for numbers of inventions, amount of investment, how many research papers are being written on this or that or the other topic. But that doesn't tell you anything. That only tells you how popular a technology is, whereas improvement rates can tell you what it will be in the future. So if we scroll back to the top one more time, from every single historical case of technological disruption that we've studied, we found that the technology with the highest improvement rate always ends up as the dominant solution. And this goes almost entirely contrary to most experts' debates in these areas, whether it's about quantum computing or whether it's about display technology or whether it's about EVs, battery chemistries, etc. At the early stages of technological emergence, the vast majority of experts will be highly skeptical. They can't possibly believe that this thing will ever compete. There's all sorts of reasons to imagine why it won't and why it's worse than other more mature solutions. That might all be true, but the fact is that we've never been able to identify a single case of historical technological disruption where it wasn't the fastest improving technology according to our metrics that ended up as the dominant solution in the field.
Okay. And as I was saying, we can find other proof that topological qubits are actually going to be the future, because we can research specifically the error correction strategies that are usually used. And error correction is one of the main topics when it comes to quantum computing. And that's because the biggest problem that nowadays qubits have in modern quantum computing is that they are prone to decoherence. So they, due to environmental factors like heat and vibration, they tend to collapse into a simple qubit, a simple bit. So they collapse in either a 1 or a 0. And the traditional error correction strategy is active quantum error correction, but as you can see, it's not improving very fast compared to non-abelian onions, which are the type of error correction strategy that Microsoft is using. And specifically, they work by storing information not in a specific single fragile particle, but encoding this information in the motion patterns. And so they become naturally resistant to error. And this is at the core of Microsoft invention. And as you can see, it's improving much faster than traditional error correction, which can open up the path to whole new capabilities in quantum computing.
All right, so we have a question. When it's a slow-moving tech that's quietly building steam, how would you pick the winner then? So whether technologies improve fast or slow doesn't really matter, as long as it's improving faster than what it's competing with. So you'll always find that certain technologies are improving a lot faster than others, simply by virtue of external factors. So, for example, if you take a look at software, software is comparatively tremendously easy to develop, because it costs almost nothing. I don't need a whole factory to build it. I can have a bunch of developers and they can iterate 15 times in a day and just try stuff and see what works and then improve on it. If you compare that to something like a nuclear reactor, if I want a better design for a nuclear reactor, I first need to spend a whole lot of time designing it to make really sure that it's safe. Then I need all sorts of improvements from commissions and legal entities to make sure that I can build it. Then if I want to start building it, I'll get into all sorts of lawsuits and other trouble. And so it takes forever to make a single iteration. So it's not fair to compare software development to nuclear reactors, because they're two completely different things, and one will improve a lot faster than others. So you want to compare apples to apples, such as, in this case, various approaches to quantum computing. Then the fastest improving one will win. If you have much slower improving technologies, such as the nuclear reactor types, you want to compare them with one another, and those improvement rates will be much lower. But nevertheless, the one out of them that has the highest improvement rate tends to turn into the winner.
Can I go back to that?
Yeah. Right. So Raymond is asking, if we look back at 2008, topological wouldn't be the winner. Yeah, that's true. So what we've developed is a statistical method that looks at, out of all the patents that were published in a certain year, what is the cycle time and what is the knowledge flow. So for topological as a whole, I believe we have not that many inventions, like a couple hundred.
Yeah.
Yeah, a few hundred. And it hasn't been in the picture for that long. So here you can see the first inventions are filed in 2004, which means that in the very beginning, there's only a handful of patents. And if there's only a handful of patents and there's one patent that is an outlier when it comes to either cycle time or knowledge flow, it can really pull the improvement rate in a certain direction. So it's not uncommon to see an early stage technology that is a bit jumpy. But as more patents accumulate, the metric will stabilize itself. And in this case, you can see that for the vast majority of time, topological has been on top. And in that case, every single time we've seen that, it turns into the winner in the end. Does that make sense, Raymond?
I think I can use my mic, right?
Yeah, for sure.
Yeah. Okay. Yeah, I understand what you're saying. At the same time, I know that knowledge now, because now it's 2025. But if I just kind of go back to 2008 and would have made a snapshot at that time, I would probably then not have chosen that topological technology. And for example, the neutral atoms, which are very low at that period, right? They are really at the bottom. If I look at them today, they are, kind of second in line. So, yeah, I'm a bit struggling with understanding how you, how you then can prevent betting on the wrong horse.
Yeah, no, that makes sense. So yeah, if you want to make really, 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 really early stage bets, so imagine we're back in 2000, topological quantum computing isn't even a thing, because no one's even attempting it. Then we would have made a different recommendation, because we can only tell you what the data says, which is why it's so important to continuously do this, because like you can think of it as an early warning system. So what we cannot tell you is that tomorrow a completely new approach to quantum computing will be invented, which in turn will start improving a lot faster than what there already is. But if you're in a game of capital allocation, which most large corporates, but also governments and even smaller organizations are, you want to reduce the risk that you're betting on the wrong horse, and you can never entirely rule it out. But if you want an early warning system of what is improving the fastest, and given the current state of affairs, what is the most likely to win in the future, then this is your best bet. So even like now, for example, with all of the controversy around topological quantum computing, you see that time and time and time again. Most corporations, when they do get into developing a new technology, will not be the pioneers, but they will be early adopters that jump on the bandwagon, and especially in those scenarios, this can be really powerful.
Mm-hmm. Okay, thank you.
Right. I think, Sunanda, we already sort of asked or answered that question.
Any other questions? Okay. Then, staying on the topic of what could potentially be next in quantum computing, we can talk about some new quantum technologies that are emerging and that are on the radar for future developments. Specifically, we have a list of emerging technologies, and what we can do at this early stage is harnessing the power of AI to learn more about them and understanding which direction they are going. So, for example, we can pick one of them, defect-based qubits. And what we can do is use a feature of our platform that is called Chat with Set, where we can learn more by Q&Aing the whole pool and the whole data set of patterns. So, for example, in this case, we can ask what materials are mainly used for defect-based qubits. And since defect-based qubits basically store information in imperfection of solid materials, we can ask which are the more popular materials that are used for this new type of quantum computing. So the AI is reading all the patterns and will give us a response and an answer based on these patterns. So we can see that diamond is a popular choice. as well as silicon carbide, and of course, semiconductors and other materials. And just like that, you can simply Q&A the patterns of a technological area that you're interested in, and you can get fast and precise answer based on real pattern data and not just generated by the LLM in this case. Any question?
Cool. All right. Thank you very much, everyone. And please keep your eyes and ears open for the next webinar that we'll announce shortly on a completely new technological topic. Thanks a lot for joining us, and see you next time.